So, we will start this lecture by looking back at one of the problems that we had discussed earlier, namely the problem of routing from one node to another. So, remember that in that lecture we had learnt how to develop routing algorithms for routing through shortest paths, right. And I had mentioned that besides shortest paths there are many other metrics for defining the quality of routing. So, among those one of the most important ones is routing along minimum congested paths, because when you have a path and you have varying amount of bandwidths in the links on the path, then the amount of flow through that path is determined by the link which has minimum bandwidth among all those links, right. So, for example, that if I have a path and let us say that this has bandwidth of A, B and C, then the total flow through this has a bandwidth of minimum of A, B and C, right, because the one which is the thinnest becomes the bottleneck and determines the amount of flow that is possible along this path, right. Now, when we talk about congestion, congestion is just the reverse of this, because if A is the bandwidth, then we can say that 1 by A represents the congestion, okay. So, the more congested means the less the bandwidth is available, okay. Now, suppose our task is to route packets from some source S to some destination T along a path which has the minimum total congestion. Now, what do we mean by congestion? So, if there is different amount of congestion on the links, then the most congested one determines the quality of the path, okay. So, if the congestions are x, y, w and v, then the congestion of the path, the congestion on the path from S to T is the max of this x, y, w and v, right. So, unlike in the shortest path case where we were adding up all of these to determine the quality of the path, that is in shortest path the quality of this path would have been x plus y plus w plus v. Here instead of that, the quality of the path is max of the weights of the edges, right. Now, can you tell me that this problem can be solved using what method? It reduces to a very standard well known problem with which all of you are familiar. How do I determine the minimum congestion paths? No, it is easier than that. See, what we are trying to minimize is, we are trying to find a path which has minimum cost, and the cost of a path is given by the maximum of the edge weights on the path, right. So, this is a property which a very standard type of structure guarantees us, and that is the minimum spanning tree, okay. So, first let us understand that why is a path along the minimum spanning tree guaranteed to give us the minimum congestion path from a source to a destination, right. So, let us look at a proof of that. So, to prove that, suppose we have a node S and we have a node T, and the spanning tree path, the path on the spanning tree from S to T is like this. Okay. This is the path on the minimum spanning tree from S to T. So, by definition a spanning tree has a path from every node to every other node, and because it is a tree there is only one such path. So, this is the path from S to T in the minimum spanning tree, right. So, each of these edges has some weight, and the bandwidth of the congestion of this path is determined by the edge having maximum weight. So, let us say that this edge having weight W is the maximum weight edge on the path from S to T in the spanning tree, right. So, this is the path on spanning tree and this is the maximum weight edge on the path. Okay. Now, what is going to happen if I remove this edge from the tree? No, no, no. The tree will become partitioned into two sets, two trees, right. So, this side will be one tree, this side will be one tree. So, I have some vertices on this side, some vertices on this side, right. Okay. Now, suppose from between the vertices on this side and the vertices of this side, there are other edges which are not in the spanning tree. Okay. In the graph, there can be other edges between these which are not there in the spanning tree. So, let us say that there is an edge between these two. Okay. There are other vertices here, and there can be edges between those vertices, right. So, if you take out W and put in any of these other edges, you will get another spanning tree, right, because the edge W, when you remove it, the set of vertices in the spanning tree get separated into a set S and a set T, right, where this S belongs to S, this T belongs to T. Now, if you add any edge from a vertex in S to a vertex in T, it will reconstruct the tree, you will get another spanning tree, right. Okay. Now, one of these edges will have to be in the spanning tree, otherwise how can you have a path from S to T if none of these edges are there, because if none of these edges are there, there is no bridge between the vertices in S and the vertices in T. So, at least one of these edges will have to be there, right. Now, what I claim is that among the edges that are going from S to T, W is the one having the minimum cost. Why? Because if there was any other edge which has a cost less than W, then I could have removed W and put that in and got a spanning tree of lesser cost. It could be the only edge also. But if there is any other edge, that edge will also have cost at least W, right. In other words, there cannot be any edge having cost less than W from a vertex in S to a vertex in T, because then we can replace W by that edge and get a tree of lesser cost, which is not possible because this is the minimum spanning tree. Okay. But what does this mean? It means that if you have to go from S to T, then you will have to cross this bridge from S to T, and among all bridges from S to T, the one which has minimum cost is W. So, every other path from S to T will have cost at least W, because W is the maximum on this path, and every other edge that you take having cost greater than W will make the path cost of the other paths to be at least as much as W, right. Therefore, the path along the minimum spanning tree from S to T is the path which has the minimum congestion.
Surely greater than W.
Mm-hmm.
Surely the greater than W, because the multiple edges are not.
I didn't get your question.
Node V and U, we have a edge between U and V.
Mm-hmm. You mean to say that this is U?
Yes.
This is U, this is V.
Yes.
Okay.
And then W is the weight between these two.
Right,
edges.
right.
And then there is no edge from U to W directly.
There
So
is no edge from U to
V directly, because W is one edge.
Yeah, this is one edge.
Then other edges come from the S to T, which is not belong to U to V.
No, between U and V you can have only one edge,
Yeah.
because in a normal graph.
Any other edges which is connected to S to V, S to T, may have always great weight standard.
Yeah, all of these what we have shown is that all edges that go from a vertex in S to a vertex in T will have weight at least W. Why? Because suppose there is an edge which has a cost of say A, and let us say A is less than W, then what you can do is you take out W from the tree and put in A, and then you will get a spanning tree of lesser cost. But then we started by saying that this is a path in the minimum spanning tree. So, how can we have a spanning tree of lesser cost, right. So, therefore, all of these edges will have cost at least W or more. Is that clear? So, therefore, for going from S to T, every path will have cost of at least W, right. So, the path along the minimum spanning tree is one which has the minimum congestion. Is it clear? Mm-hmm.
Of weight which was greater than W,
Yes.
but less than the path weight from S to V.
Yeah. Could be.
Then
But see, that is not going to belong to the minimum spanning tree, because if suppose this has a cost of B, if B is greater than W, then W will be there in the minimum spanning tree, not B. And the congestion on your path from S to V to this will have more congestion, because B is greater than W. You see, it is not the sum of the edges, it is the max of the edges, right. So, this gives us a motivation for understanding that why we need minimum spanning trees in a distributed system. So, what we are going to study now is our distributed algorithms for finding minimal spanning trees. Remember that we had previously studied algorithms for finding out spanning trees. For example, the echo algorithm is an algorithm which finds a spanning tree, the traversal algorithms find spanning tree, but here we are interested in finding out minimum spanning trees. Okay. So, let us see how this works. Now, there is a very close relationship between leader election and spanning trees. Okay. To demonstrate that, let us look at this, that let CE be the message complexity of the election problem. Remember, we are talking about the message complexity of the problem. Okay. So, these are lower bounds, okay, and CT be the message complexity of finding a spanning tree. Okay. Now, given a spanning tree, we can run the election algorithm on trees. Remember, we studied one algorithm where given a tree, you run election on that, and that algorithm finds a leader in order n time. Okay. So, therefore, we can say that because given a spanning tree, we run election algorithm on the tree to find a leader in order n time. So, we can say that CE, the number of messages to elect a leader, is upper bounded by CT, the number of messages to construct a spanning tree, plus order n time to run this election algorithm, right. And also, given a leader, we can run the echo algorithm to find a spanning tree with 2E messages, right. So, we can say that CT is less than or equal to CE plus 2E. This one? Okay, suppose I give you a spanning tree, then remember that we had studied one algorithm which does election of a leader in a tree. That algorithm runs in order n time. So, if I give you a spanning tree, then you can run that order n algorithm. So, the total time for election or the total number of messages for election is the number of messages that you spent in constructing the spanning tree plus the order n messages for running the election algorithm on trees. Okay. So, you have an algorithm which can give you a leader in CT plus ON number of messages, right. So, therefore, this is an upper bound on the message complexity of the election problem.
Message complexity of algorithm?
No, the problem. CE is the message complexity of the election problem, meaning that you cannot have any algorithm for election having less than CE number of messages. Okay. So, it is a lower bound. Similarly, CT is the lower bound on the number of messages to find a spanning tree. Okay. Now, if you look at these two inequalities, then and compound that with this result, which I did not prove earlier, is that any comparison based election algorithm for arbitrary networks has a worst case and average case message complexity of at least E plus n log n. So, the election algorithm, comparison based election algorithm, what do you mean by comparison based election algorithms? That is, each node has an ID and we want to compare the IDs and come up with the elect the leader having minimum or maximum ID. Okay, that is comparison based election. Now, this lower bound states that you cannot have an election algorithm which is going to perform better than E plus n log n. Okay. Now, if you take this and take these two inequalities, then we see that the two problems here are of the same order of magnitude. Why? Because the CE is lower bounded by E plus n log n, right. So, when you add 2E to that, then that is also lower bounded by E plus n log n. Okay. So, therefore, CT is upper bounded by this complexity E plus n log n. Okay.
Sir, in general, E is n square.
E is about n square, yes. So, we are just saying E.
So, why sir E plus n log n?
No, this is a result that we have not proved, but this is a result which exists. Okay, there is a proof for this result.
N square.
No, E does not necessarily have to be n square. It depends on the kind of graph that you have. Like for a tree, E is order n, right. And then again, if you substitute CE with this here, then you see that CT is greater than or equal to order of E plus n log n. So, therefore, we see that CT is bounded on both sides by E plus n log n, and therefore, it also has a complexity of E plus n log n, right. So, that shows that both the election algorithm and the spanning tree algorithm are of the same order of magnitude. Okay. Now, this was the comparison between leader election and finding a spanning tree. Okay. Now, what we are going to see is how do we find a minimum spanning tree, okay, which is obviously a different problem. So, the definition of the minimum spanning tree given formally here is as follows, that let G equal to V comma E be a weighted graph where WE denotes the weight of AG. The weight of a spanning tree T of G equals the sum of the weights of the n minus 1 edges contained in T. It is the sum of the weights of the edges, that is the weight of the spanning tree, and T is called the minimal spanning tree if no spanning tree has smaller weight than T. Okay. And now, let us understand this result, that if all edge weights are different, then there is only one MST. So, if all edge weights are different, then the minimum spanning tree is unique. So, you don't need to say minimal spanning tree anymore, you can say it is a minimum spanning tree. Okay. Now, can you establish that if all edge weights are different, there is only one MST? How?
Minimum spanning tree with any other edge which is not in the tree, the edge will be, the weight of the tree will be different and greater than
Yeah, so you say you can give the proof like this, that you start by examining, suppose let us go by contradiction. Suppose there are two MSTs. Okay. Now, take any one of them. Okay. Take any one of them and start comparing the edges on the basis of increasing weight. Okay. So, suppose you get the edge E. Now, edge E is there in both T and T dash. So, T is one minimum spanning tree, T dash is another minimum spanning tree. So, E1 is there in both of them. Okay. E2 is there in both of them. And then there will be some place where some edge is some edge weight is here, but not there. So, suppose at some point we find that I have EI here in the ascending order, and in the ascending order here in the same place I have EJ. So, this is the first place where the two trees have differed. Okay. What have I done? I have sequenced the edges of T in ascending order of weight, I have sequenced the edges of T dash in ascending order of weight, and I am comparing the two sequences, and I have found that this is the first place where the edge in T and the edge in T dash are different. Okay. Now, without loss of generality, let us say that the weight of the edge EI is less than the weight of the of this. Okay. Now, let us see one thing. My claim is that if this is the case, then T dash cannot be a minimum spanning tree. How are we going to show that? Take out the edge EJ from here. Okay. And then what are we going to do? How do I know that putting EI there is going to okay. Let us look at it the other way round. See, EI is not there in T dash, right? Okay. Now, if I put ei in T dash, it will create a cycle, right. Let this be the cycle. ei is there in this cycle. Now, these edges, all of them cannot be in T, because then T will also have the cycle, right. All of them cannot be in T, right. Now, suppose there is one of them which is not in T, okay, and let us say that that edge is A, this is not in T, okay. Now, if this is not in T, then this cost of this edge will be more than these edges which we have already seen, because all of these edges are both in T and T dash. So, A is not in these edges, so A is somewhere on this side. So, the weight of A is more than that of ei, right. Then what can I do in T dash? In T dash I can put ei and take out A and get another tree having lesser cost, but then T dash cannot be the minimum spanning tree, right. So, we conclude that if all the edge weights are different, then there is only one minimum spanning tree. In our algorithm, we will assume that all edge weights are different, okay, and the distributed algorithm that we will study now will work on the assumption that all edge weights are different. It is important to understand the notion of a fragment in a minimum spanning tree algorithm. A fragment is a subtree of a MST. Okay, it is a subtree of the minimum spanning tree. If F is a fragment and E is the least weight outgoing edge of F, then F union E is a fragment, right. What does this say? Suppose this is the subtree of a minimum spanning tree, right. If I look at all the edges which are coming out of this, all the edges which are coming out of this fragment, then the minimum of these will have to belong to the spanning tree. It is because of the same reasoning that we did earlier, right. So, because this is two partitions of the vertices, so among these edges the minimum one has to be in the spanning tree, okay. So, if F is a fragment and E is the least weight outgoing edge of F, then F union E is another fragment. Now, the two well known algorithms for minimum spanning tree, they the way in which they handle these fragments is different. So, Prim's algorithm starts with a single fragment and enlarges it in each step with the lowest weight outgoing edge of the current fragment, and Kruskal's algorithm starts with a collection of single node fragments and merges fragments by adding the lowest weight outgoing edge of some fragment, okay. So, remember how Kruskal's algorithm works. It starts with the minimum cost edge, which basically joins two fragments at level 0, right, and then picks up the next minimum cost weight edge and then sees whether it joins two fragments. If so, it puts it in. So, in each step it checks whether the next edge in order of increasing weight is an outgoing edge from some fragment or whether it is an internal edge. If it is an internal edge, it is discarded, otherwise it is used to join two fragments, That is how Kruskal's algorithm works. Now, given these two algorithms, which one do you think is better in a distributed setting? So, we have a divided opinion. Some people are saying Prim's, some people are saying Kruskal's. Which one is more amenable for parallelism? Kruskal's, because in a distributed way the fragments can start merging and then merge with each other to form the spanning tree, right. So, when these two fragments are merging and these two fragments are merging, that can happen in parallel, right. So, Kruskal's is, therefore, there are certain interesting things about Kruskal's which makes it interesting to see how we can adapt it to the distributed setting. And the algorithm that we are going to study is an extension of Kruskal's in the distributed setting. The algorithm is called Gallagher-Humblet-Spira algorithm. It is a distributed algorithm based on the philosophy of Kruskal's algorithm. There are certain assumptions that we make in this algorithm, namely that each edge E has a unique edge weight WE. So, all edges have unique weight. All nodes, though initially asleep, they awaken before they start the execution of the algorithm, and the awakening can take place by a message from some neighbor. So, when a process is woken up by a message, it first executes the local initialization procedure, then processes the message. Okay. So, initially processes will be asleep. Okay. When the algorithm's initiation starts, then the nodes will inform other nodes that you have to participate in the minimum spanning tree algorithm. This is the outline of the algorithm. We will go into more details progressively. It is one of the most involved and non-trivial wave algorithms. So, there are a lot of things that will happen. So, let us go systematically. We start with each node as a one node fragment. So, each node initially is a one node fragment. The nodes in a fragment at any point of time will cooperate to find the lowest weight outgoing edge of the fragment. Okay. So, initially when you start with a one node fragment, what is the lowest weight outgoing edge? It is the lowest weight edge incident on that node, right. So, that is how it will start, and subsequently at any point of time a fragment will cooperate to find out the lowest weight outgoing edge, right. And when the lowest weight outgoing edge of a fragment is known or has been identified, the fragment will be combined with another fragment by adding the outgoing edge to the tree in cooperation with the other fragment. Okay. So, the two fragments will join to form a larger fragment. The algorithm terminates when only one fragment remains. That means that the whole spanning tree has been discovered. Here are some notations and definitions. Firstly, we will have a fragment name. So, to determine whether an edge is an outgoing edge, we need to give each fragment a name. Why do we need to have a fragment name to identify whether it is a outgoing edge or a internal edge? So, basically to test whether an edge is an outgoing edge from P, P will send a test message to Q, okay, and Q, and on that message we will have the ID or the name of P's fragment. So, P knows which fragment it belongs to. So, P will send a test message with that fragment name. Now, what Q will see is that does the fragment name on the message match with my fragment name? If yes, then this means that this is a edge from a node in the same fragment. What will happen if you put that edge in the tree? It will create a cycle, right. So, we won't accept the test. So, we will reject that. we will say that this branch cannot be a branch of the tree, okay, and forever reject that branch. Okay. The edge PQ will be rejected forever if it is found that P and Q are in the same fragment, right. That is why we need the fragment names. Each fragment is assigned a level which is initially 0 for an initial one node fragment. So, think of it like this, that initially I have n fragments, each having one node. Okay. When two fragments of the same level join, they will create a fragment of the next higher level. Okay. So, two fragments of level I will join to form a fragment of level I plus 1. Okay. So, in the ideal case, how many fragments, how many levels will we have? Log n. Right. So, in the how will it be 1? Because you see, it is going to start with n fragments. No, then you will have n levels. In that case, you will have n levels. What is happening is, see, two fragments at level I, when they combine, that is giving you a fragment at level I plus 1.
Assume that nodes were 1, 2, 3. The neighbor of 1 having minimum cost with 2 and 2 is with 3 and 3 is with 4. Just after one iteration, it will, everyone will be connected and n minus 1 edge will be connected.
No. See, the merging is going to take 2 at a time. Okay. So, it is not that when 1 is going to merge with 2, 2 is going to merge with 3, that kind of thing will not happen.
But finding out the minimum for each fragment can happen parallelly.
Yeah, but when they join, they will just increase the level by 1. So, what I am saying is that log n is the okay, by log n number of levels we should be able to merge the 3, order of log n number of levels. So, what this algorithm will guarantee is that the number of levels that we need will be order of log n. Okay.
The graph is already a spanning tree. The graph is already a spanning tree.
So, we will see those pathological cases separately. Now, combining large and small fragments. The smaller level fragment combines into the larger level fragment by adopting the fragment name and the level of the larger fragment. Now, see, we are imposing a kind of partial order here. We will allow smaller fragments to combine into the larger fragments, but not the larger fragment to combine into the smaller fragment. And the reason for this is to make sure that there is no concurrency problem, because the algorithm will run in a distributed fashion. I will give you the exact situations under which if we did not have this restriction, we would run into trouble, right. Remember that this is completely distributed, we do not have any centralized control over what is happening, right, and that has different kinds of concurrency problems. We will see them during the course of this discussion. So, that is why we purposefully impose a restriction that smaller fragments will combine into the larger fragments, larger fragments will not combine into smaller fragments, and when fragments of the same level combine to form a fragment of a level which is one higher than the two fragments. Okay. In the case where the smaller fragment combines into the larger fragment, larger level fragment, the smaller fragment will adopt the name of the larger one and will also inherit the level of the larger one. Okay. So, if I have a level 4 fragment and the level 2 fragment merges with the level 4 fragment, then the whole fragment will have level 4 and the name of the level 4 fragment will become the name of the whole fragment. Okay. On the other hand, when two fragments of the same level are merging, so this is one fragment. What is a fragment? A subtree, right? And this is another fragment. These are in the same level. Okay. When they merge, they will merge by adding an edge between them. Okay. We will call this edge, the edge with which they merge, as the core edge of the new fragment. Okay. We will call this the core edge of the new fragment, and if this was level k, this was level k, then this one, the integrated one, this one will have level k plus 1, and the name of this will be the weight of this. So, suppose this is P, this is Q, and this is the weight of PQ, then the name of this is this. Okay. This is what we are doing. We have decided to do this in the algorithm. Okay. And we will see how this becomes useful. But is it clear what is happening here? If one of this was of a smaller level, then the integrated fragment would still have been level k, the larger of the two, and the name of the fragment would have remained the same as the name of the fragment of level k. Okay. Right. And also just remember one thing is that the edge which got added for merging the two fragments when the two are equal is called the core edge. Remember, just remember that is a core edge of the fragment. Okay. So, this is the summary of the combining strategy. A fragment F with name Fn and level L is denoted as F equal to Fn comma L. Okay. Let EF denote the lowest weight outgoing edge of F. Okay. This is fragment name, this is level, and let EF denote the lowest weight outgoing edge of F. There are three rules for combination. Rule A: if EF leads to a fragment F dash equal to Fn dash L dash with L less than L dash, okay. So, the smaller fragment is trying to merge with the larger one, then the smaller fragment F combines into F dash, after which the new fragment has name Fn dash and level F dash. These new values are sent to all processes in F. Yeah.
The level of the new combined
is L dash. Did I write something else? Oh, no. Did I? Is there some problem here?
The name you have written here, level F dash, that should be level L dash.
Oh, sorry. Yeah, this should be instead of F dash, this should be L dash. Yeah, that's a typo. Okay. Has a new fragment as name Fn dash and level L dash. Yes. These new values are sent to all processes in F. If EF leads to a fragment F dash, okay, this one again became wet. just excuse me for a moment, let me correct this one, otherwise every time this is going to show up. Yeah. If EF leads to a fragment F dash with L equal to L dash and EF dash equal to EF, okay, the two fragments combine into a new fragment with level L plus 1 and name WEF. These new values are sent to all processes in F and F dash. So, the way this is going to work is that both the node P, which is on one side of EF, will send a connect message to the node Q on the other side of EF, right. And if the fragment F dash also determines the same edge to be the lowest outgoing edge, then that one will also send a connect message along the same edge from Q to P. When both of these are there, then they decide that these are to be merged. Okay, that is how it is going to work in the algorithm, and they will combine into a new fragment with level L plus 1 and name the weight of EF. Okay. Now, these new values are sent to all processes in F and F dash by the two processes P and Q, which are on two sides of EF, right. They will come to a decision that this edge between P and Q should be edge of the tree, and then they will communicate with their respective sides of the tree to increase the level number and pass on the name, which is equal to this W of EF, right.
Does a smaller level necessarily indicate a smaller size?
No, the smaller level does not necessarily mean a smaller size. Okay. So, we will stop this lecture at this point of time. When we resume, we will again recap this and then start going deeper into the algorithm, into the more finer details of the algorithm.